Topological data analysis is a new and vastly growing branch of applied mathematics. Data analysis is of extreme importance in almost all areas of modern applied science. However, to extract information from real data, which are usually large, high-dimensional, incomplete and noisy, is challenging. TDA provides a general framework to analyze data, being successful in coordinate freeness, insensitive to particular metric, dimension reduction and robustness to noise. Beyond, it inherits functorality, one of the keys to the modern mathematics, from its topological nature, which makes it adaptive to new tools from mathematics. The initial motivation is to study the shape of data. TDA has combined algebraic topology and other tools from pure mathematics to give mathematically strict and quantitative study of shape. The main tool is persistent homology, a modified concept of homology group. Nowadays, this area has been proven to be successful in practice. It has been applied to many types of data input, and different data resource and numerous fields. Moreover, its mathematical foundation is also of theoretical importance to mathematics itself. Its unique features make it a promising bridge between topology and geometry. Basic theory, basic concepts and theoretical results in TDA will be introduced. Especially, the focus would be on the standard paradigm, namely the barcode of point clouds. These results are widely used in applications. For the basic concepts of algebraic topology, please refer to Section 2 of Carlson for a short introduction, or to the standard textbooks, such as Hatcher. Intuition. The intuition is that shape matters. Real data in high dimension is always sparse, and has some relevant low-dimensional features. The task of TDA is to precisely characterize this observation. One illustrative example is a predator-prey system governed by a Lockar-Volterra equation. One can easily observe that data forms a closed circle, which is intuitively the shape of this data. TDA provides tools to detect such recurrent movement. Lacking prior knowledge, selection of the threshold of a parameter is blind. The main insight of persistent homology is to grab all the information obtained from all values of a parameter. Of course, this insight alone is easy to make. The hard part is encoding this huge amount of information into an understandable and easy to represent way. With TDA, there is a mathematical interpretation when the information is a homology group. A common belief in this community is that true features would last longer. Short persistence is nothing but noise, though no mathematical justification is made. The topological information can be inferred from the selected long-lasting features. Early history. The idea of persistence emerged independently in three groups. Patricio Frassini introduced size function, which is equivalent to the zeroth persistent homology. Vanessa Robbins studied the images of homomorphisms induced by inclusion. Edelsbrunner et al. Introduced persistent homology together with a efficient algorithm and the presentation as persistent diagram. Carlson et al. Reformulated their definition of persistent homology and gave an equivalent visualization method called persistent barcodes. Carlson has interpreted it into the language of commutative algebra. Concepts in widely used concepts are introduced below. Note that some definitions may vary from author to author. Point cloud is defined as a finite set of points in some Euclidean space. Check complex is defined as the nerve of the cover of balls of a fixed radius around each point in the point cloud. Persistence module indexed by is defined as a vector space for each, and a linear map whenever, such that for all and whenever persistence homology group is defined as, where is the check complex of radius of the point cloud and is the homology group. Persistence barcodes is a multi-set of intervals in, and persistence diagram is points in. Wasserstein distance between two persistent diagram and is defined as where and ranges over bijections between in. Please refer to Figure 3.1 in Munch for illustration. Bottleneck distance is defined as which clearly is a special case when in Wasserstein distance. Basic property structural theorem. The first form of classification theorem for persistent homology appeared in 2005. For a finitely generated persistent module with field coefficients, this theorem also has an intuitive explanation. The free parts correspond to the homology generators, appear at radius and never disappear, while the torsion parts correspond to those appear at radius and last for. Its visualization is through barcode or diagram. Please refer to the further reading for illustrations, due to issue of copyrights. Barcode also has its root in mathematics, though not at first sight. Essentially, the derived category of chain complexes over a field is equivalent to the graded category of vector spaces. Stability. The interpretation of the mathematical concept stability in data analysis is robustness against noise. It has been that if be any space which is homeomorphic to a simplicial complex, and suppose a continuous tame functions, then the persistence vector spaces are finitely presented, and workflow. The basic workflow in TDA is: let be a point cloud, replace a point cloud with a nested family of simplicial complexes, indexed by a parameter. This process converts the point cloud into a persistent module. Apply the structural theorem to provide a parameterized version of Betty number, persistence diagram, or equivalently, barcode. Graphically speaking, computation. The applied mathematics has to face the issue of computational complexity. The first algorithm of persistent homology over as given by Edelsbrunner et al., Carlson et al., gives the first practical algorithm to compute the persistent homology over all fields. Edelsbrunner and Herrera's book serves as a great general guidance on computational topology. One issue concerning computation is the choice of complex. Check complex and Vietoris-Rips complex are most natural at first glance. However, the computation complexity would be same as matrix multiplication. It is straightforward that Vietoris-Rips complex is preferred over check complex by their definitions, and check complex does require some efforts to make a general definition in metric space. Efficient ways to lower the computational cost have been studied. For example, alpha complex and witness complex are invented to reduce the dimension of complexes. Two methods of theoretical novelty appeared recently. Discrete Morse theory has shown its potential in the computation because it may reduce a given complex to a much smaller cellular complex which is homotopic to the original one. The basic idea of another algorithm is to ignore the homology classes of low persistence. Various software packages are available, such as JavaPlex, Dionysus, Perseus, FAT, and Goody. A comparison between these tools is done by Otter et al. Also, an R package TDA is capable of calculating recently invented concepts like landscape and kernel distance estimator. Visualization. High-dimensional data is impossible to visualize directly. Many methods have been invented to extract a low-dimensional structure from the data set, such as principal component analysis and multidimensional scaling. However, it is important to note that the very question is ill-posed, since different topological features can be found in the same data set. Thus, this technique is of central importance to TDA, although it doesn't involve the use of persistent homology. Carlson et al. Have proposed a general method called mapper. It inherits the idea of Surrey that covering homotopy. A generalized definition of mapper is that let N be topological spaces and let be a continuous map. Let be a finite open covering of. The mapper is defined as the nerve of the pullback cover. This is a very general concept, which REEB graph and merged trees are special cases. Note that this is not that original definition. Carlson et al. Chooses OR, and covers it with at most two would intersect. By doing so, the mapper would be in the form of a complex network. Because the samples would be finite, some clustering methods, for example, single linkage clustering, are required to form components of the inverse map of a single cover, which is similar to the connected components if, mathematically speaking, this is a variation of REEB graph. A mathematical jurisdiction is that if the E is at most one-dimensional, then for each, the flexibility also has disadvantages. One problem is instability, that some change of the choice of the cover can lead to major change of the mapper. Some works are devoted to overcome this problem. 3 successful applications of mapper can be found in Carlson al. A comment of these applications on this paper by J. Curry is that, a common feature of interest in applications is the presence of flares or tendrils. A good software of mapper is free available online, written by Daniel Molnar and Aravind Akshan Babu.